Alright, hi everyone. Welcome to this video where we'll be learning about how to construct chemical equations from scratch, right? So before I go on further, I would like to just apologize in advance in case there's any loud noises that come from this video as there's a renovation that's going on around my place. Okay, so try to focus and if it gets very distracting, just replay the video so that you can catch what I'm trying to say. Alright, so on your notes that you have received so far, you should have seen this page that we're talking about in terms of constructing chemical equation. Now, but before we go into how to write chemical equation, we do need to be familiar with how to interpret chemical formula to determine the number of atoms. Now, what do I mean by that? Now, on this page, you'll see quite a number of notation shown on the left hand side of the column, right? And as well as on the right hand side, asking you to number the number of atoms. So what do I mean is, if you look at the first example here for the H, right? When you see this symbol of H, what does it actually mean to us? It means that there is actually one hydrogen atom, right? Then when you see it as 2H, you know that this is a coefficient. It means that we times it in, and that will be 2 hydrogen atoms. H2 means one molecule of hydrogen, but it's actually made of two atoms of hydrogen, right? So it looks like this. 2H2 means that there's two molecules of hydrogen, which means that there's actually four atoms of hydrogen, which means it looks something like this, right? As you go on and on, you should be able to construct the rest of it by yourself, right? So I'm just not going to run through every single thing, but if I can, I will jump straight to the last one of the table, but do remember to fill the rest of things by yourself. Okay, let's take a look at the last one here for this 3C2H5OH. This is what we term as ethanol, right? It's a type of alcohol, it's an organic compound, right? So based on this notation, it means that there's actually three molecules of ethanol. Now, how many atoms of carbon are there? You do need to take the 3 and you need to multiply in to see what's the total number. So if you look at the formula itself, you realize that there is actually 2 carbon, but with this 3 at the outside, this would mean that there's actually a total of 6 atoms of carbon, right? So 3 times 2, right? Then let's go look at hydrogen. When you look at hydrogen, you realize that same thing, this 3 need to times inside, but if you count the number of hydrogen, I'm just going to use a highlighter to show you, there's 5 here, and there's actually a 1 here. Now, in chemistry, we don't put 1, right? We just represent it by the symbol of H, right? So in this case, there's a total of 6 hydrogen here, but because of the number 3 outside, it's actually 18, right? So I just put a bracket here to show you, it's actually 3 times 6. Now, how many oxygen are there? Similarly, if you look at the formula, there's only one oxygen shown over here. So we just take the 3 and then we multiply in, and this should give us the 3 atoms of oxygen, right? So I hope this is a bit clearer for you in terms of what you're looking at. Of course, if you were to draw this out, right, see like the top when I draw the hydrogen, it's a lot easier because it's only a few circles. But when it comes to this, right, it gets more complicated. So if I really were to draw this out as a structure, it will look something like this. Right, so of course this looks very, very complicated, right, in terms of how the structure looks like, and it's not that practical to draw it out, right? For hydrogen, I could still do it because it's easy to draw it out, but this time if I draw this out and I need to draw 3 sets of this, right, it's gonna be quite a nightmare, right, because you need to draw this thing repeatedly for 3 times. So sometimes it's a bit harder, and we do have to depend on our familiarity with these numbers here and try to multiply in. Of course, do it step by step so you can see what's going on. Okay, so that's for the first part. Now, beyond that, now those at the top of what you see in this table, these are molecules, right? So try to fill in all the blanks yourself, right? And we can check when we meet again. The next one on the next table is what about ionic compounds? Now, we know that ionic compounds, they don't exist as molecule, and we just use term the word formula unit. Now, don't need to worry too much about this. It actually means more or less the same thing. So if you see one NaOH here, it means that it is one NaOH. Right, so one formula unit of NaOH. How many of this sodium are there inside? That's one of it. How many of this oxygen is there inside? It's one of it. How many of this hydrogen inside? Is one of it, right? Based on the formula. And we see 2 NaOH, it means that there's 2 formula unit of it. How many Na are there? There's usually 2 sets. How many O are there? There's usually 2. How many H are there? It's usually 2. So you can just multiply in the 2 for everything. Right, so try to do this yourself as well, and then just calculate all the various numbers just to familiarize yourself before you go on to the next part of writing the formula. As you're running through this thing, I just thought to maybe highlight one important thing. Do take note that in ionic compounds, the particles that we're looking at are called ions. Right? I know that in this table here, they use the word atoms, which is actually conceptually not that accurate, right? Because in ionic compound, it should be about ions. But why are we using the term atom here? We are just trying to help you to count how many of these tiny circles are you looking at. Then it will help you later on when we talk about chemical equation. Okay, so do take note of this disclaimer over here first. Alright, so try to fill up everything by yourself. As mentioned, I will run through the last one as an example, right? But the rest of it, please do yourself as we will go through it when we meet again. So 2CuCO3 means that there's two formula unit of copper to carbonate, right? What we do is in terms of the number of carbon, in terms of copper, it will be 2, because we take the 2 and times in. Number of carbon, we times in, it will be 2, and number of oxygen, times in this case, it will be 6, because it's 2 times 3. Right, so this counting of atoms is important because with this, it then helps us with the idea of balancing of chemical equation. Okay, I hope everything is going on well so far. Let's take a look at the next point here. Now, in this part of the notes, you are being shown an example of what it looks like when there is actually a chemical equation. So take a while to look at this diagram, right, and try to see how the atoms, the circles, actually changes along the way. Well, I'm sure as you look at this diagram, you realize that there is some form of a rearrangement of what we are looking at in terms of how the circles are like. Just like Lego blocks, right, you realize that there's a bit of a plucking out and then reattaching them together. So what happens in a chemical reaction, most of the time, bonds will be broken. Right, bonds broken means that you're actually splitting up the atoms from where they belong to each other. Then what happens next is that the atoms actually rearrange themselves. Now, if you look at the diagram that you see on the screen, you realize that the red color circles will now actually pair up with a white color circle, and you see the different diagram as you see on the right hand side in terms of the products, right? And then this will mean that actually you form new bonds. But what's interesting in this whole process is that no atoms are lost or created in the whole process, and that would mean that whatever you start with on the left hand side and whatever you have on the right hand side will be equivalent to one another. Okay, this will mean that the total mass of the reactant is equal to the total mass of products, and that's what we call the law of conservation of mass. Okay, so in other words, the number of circles that you see on the left hand side, in terms of the type and colors of it, must be equal to the number of circles that you see on the right hand side. So that's the whole idea of balancing a chemical equation. So we're going to put this into practice, but we'll watch a few videos and also try a simulation before we go on to the individual practice on your own. Okay, but just to make sure that all of us are on the same page, you've learned this before in lower sec. Just to recap again, in every equation, there's always a left-hand side and there's always a right-hand side. Now, reactants are shown on the left-hand side, while products are shown on the right-hand side. And then this is always represented by an arrow. Why is it an arrow? Why is it not an equal? Because this is about progress. It's about a reaction. That means it's moving from one direction to another direction. Equal means that it can be either way. Okay, so must be towards a certain direction. And of course, in equations that we are learning now, chemical equations, we are no longer going to write the name of the chemical. Instead of writing reactant A, we might write something like CO for the formula. Instead of writing reactant B, you might write something like H2O instead of water. Right? So this is something that you must get used to, and that would mean that your formula must be strong and clear. Okay? And last but not least, in equation, you may sometimes come across this kind of symbol. These are called state symbols represented in a letter within a bracket. They are actually used to represent the state of the chemical. So if solid is S, if it's liquid, it's L. Okay, liquid, do take note, is also the same as molten, right? G is for gaseous, and AQ is for aqueous. Now, what does it mean when we say aqueous? Aqueous means that it's a solution. Okay, when something has dissolved already. Okay, let me just rewrite this. Okay, so this would be the 4 state symbols that you may see in the chemical equation. Right, but we don't worry about this one first. Let's worry about writing a chemical equation from scratch. So let's take a look at the video first to have a bit of a sense of what chemical equation writing should be like.
Most of the time though, instead of writing these word equations, we write symbol equations and use the chemical symbols of each molecule involved. So for our reactions here, we'd have CH4, which is methane, plus O2, going to form CO2 and H2O. Notice here though that we put O2 rather than O, and that's because oxygen exists as a molecule made up of 2 atoms. So with that in mind, Whenever you include oxygen in a reaction, you have to put O2. And similarly for chlorine, you'd put Cl2, and for nitrogen, you'd write N2. Next, let's take a look at how to balance chemical equations. If we take our equation again, it's not yet quite right because we haven't balanced it. In order to be balanced, our chemical equations need to have the same number of each type of atom on either side of the arrow. So for our example, we can see that on the left of the arrow, there's 1 carbon, 4 hydrogens, and 2 oxygens. But then on the right, there's 1 carbon, 2 hydrogens, and 3 oxygens. This means our equation's not balanced. Somehow, we need to increase the number of oxygens on the left and increase the number of hydrogens on the right. Now, it's totally fine if you can't immediately work out how to make it balance. Balancing equations is nearly always a process of trial and error where you just keep trying different numbers until you get the right answer. The first rule of balancing equations is that we can't change any of the little numbers though. This is because doing so would mean that we were changing the actual type of chemicals in our equation. As an example, if we change our O2 into an O3, we've accidentally changed it from an oxygen molecule into an ozone molecule, so an entirely different chemical substance altogether. Instead, we have to rely on changing the big numbers in front of the different elements or compounds, as this number just represents how many of that substance there are. To use oxygen as our example again, writing O2 means 1 molecule of oxygen, but writing 2O2 means 2 molecules of oxygen. And the final rule is that we have to use whole numbers rather than fractions, so we don't write things like half O2. So, looking back at our main equation, let's start by balancing the oxygens. We've got 2 oxygen atoms here on the left of the arrow, and then 3 oxygen atoms on the right. To increase the number on the left, we can write a 2 in front of the O2. Remember that we have to stick to whole numbers, giving us a total of 4 oxygen atoms on the left. At this point then, we've got 4 on the left and 3 on the right. So we need just 1 more oxygen atom on the right-hand side. Let's try adding a 2 in front of the H2O, which gives us that extra oxygen atom, but also 2 more hydrogen atoms as well. Luckily for us, we now have the same number of each type of atom on both sides of the arrow. 1 carbon, 4 hydrogens, and 4 oxygens. And so our equation is balanced. In real life, you'll often have to go through a process of trial and error, but as long as you stick to the rules, you should be fine. Let's finish up then by trying one more example. Sulfuric acid plus sodium hydroxide goes to form sodium sulfate plus water. On the left, we've got 3 hydrogens, 1 sulfur, 5 oxygens, and 1 sodium. And then on the right, we have 2 hydrogens, 1 sulfur, 5 oxygens, and 2 sodiums. Although it's up to you, I recommend balancing the least common elements first, which in this case would be sulfur and sodium. As sulfur is already balanced, with 1 on either side, I'd look at sodium, where we can see that we need 1 more on the left. To fix that, I'd just put a 2 in front of the sodium hydroxide, as that gives us the 2 sodiums that we need. Then, if we count all of our atoms again, we can see that we need 2 more hydrogens and 1 more oxygen on the right-hand side. This is a pretty common problem to have, and we can fix it by adding 1 more water molecule to the right. As always, when you think you're done, just double check everything to see that all your numbers balance. So for us, we've got 4 hydrogens, 1 sulfur, 6 oxygens, and 2 sodium atoms on each side. So our equation's exactly balanced, and we're finished.
Alright, so as you saw from the video, balancing of a chemical equation does require a bit of patience, right? You do need to count what's on the left-hand side and what's on the right-hand side. But not to worry, there are various simulations out there that can help you to visualize what's going on. So first is on your notes, there's this link over here. Can I get you to explore this link using your PLD so that we can explore the simulation together? So once you click on this link, you will be brought to this particular page, this over here, right? And then if you click on the play sign, this will open up the simulation. It's called the fact simulation, and to make it simpler, we are going to start with just intro, right? But as you move along, when you get more pro at it, you can move on to the game segment, which is the last one on the screen. Let's take a look at intro first. Now, how does intro look like? You should see this equation here. In total, there should be 3 options at the bottom: making ammonia, separating water, combusting methane, right? Each of these represents a type of chemical equation. And on the top right-hand corner, you should be able to change the view in terms of what you're looking at. But for simplicity, all of us are going to choose the one with the 3 circles. This will show us the model to count. So how do you go about writing this equation? We'll first add 1 to all the things so that we can visualize how they look like. If you don't put a 1, actually you can't see how the molecule will look like. So in this case, you realize that, hey, nitrogen looks like 2 blue circles, hydrogen looks like 2 white circles, and ammonia, which is NH3, looks like 1 blue circle with 3 white circles. Now goes with the idea of balancing. As you're counting this thing, we realize that there is more blue circle on the left hand side than the right hand side. How many more exactly? There's actually one additional one. So how do we make sure that it balances up? We do have to add in another blue one on the right hand side. But as what I saw in the video, we cannot just change the formula as and how we want, right? We do have to account for what the formula is supposed to be. And in this case, NH3 is always one blue with three white. So what we do over here is we will actually add in one more NH3, right? And then this will give us two of the blue circle. But this time round, we realize that the blue circle is fine already, but now we have actually six of the white circles. Then how do we account for the six of the white circle? We actually add in two more on the on the left hand side, and this will balance our equation. And our equation will therefore be N2 plus 3H2 arrow 2NH3. Right, when you balance it, you will see the balance symbol coming out on the left hand side of the simulation. If you replay it, you can try it out again. Let's take a look at the second one, separating water. Same thing, let's just put it as a 1 for each of them, right? This will allow us to visualize how the individual molecule looks like. And you look at it carefully, you realize that on the left hand side, there's one red circle. On the right hand side, there's two red circles. So what do we do now is we'll put a 2 in front. This will increase it to make sure that the red circle is balanced. But then now we have 4 white circles on the left hand side, but only 2 white circles on the right hand side. Then we'll put one more here, and this will ensure that the white circles are also balanced. And of course, in this case, the white circle is the H, the red circle is the O. Let's go on to the last one, combusting of methane. Now the equation gets more complicated, right? Because there's now 4 different formulas, but let's just put it out one by one first, right? So this will allow us to see how the diagram looks like for each of the model. And if you count it properly, you realize that this time around, there are quite a number of things that we need to balance. First, let's take a look at the gray circle. Now, the gray circle represents carbon. On the left and the right, they are both 1, which is good. The white circle represents H. On the left hand side, there's 4. On the right hand side, there's 2. So what I can do is we can actually increase this amount to 2. Then this will actually change it to left hand side, there's 4 white circle. Right hand side, there's also 4 white circle. Then we go on to the red circle. On the left hand side, there's 2 of them. And on the right hand side, there is actually 4, right? If you count it, there is 2 in CO2, and then now there's the 2 red circle for the 2H2O. And to balance this, we have to add in these 2 over here. And there you have it. That's how you actually balance a chemical equation using a simulation like this. Now you should actually try to balance this over and over again, taking your own time, so that you can see for yourself how it will look like. And of course, as I mentioned, go to the game segment. There's actually a total of 15 different chemical equations over here for you to practice and get to familiarize yourself with the balance of equation. And it goes from level 1 to level 3 in terms of difficulty. So maybe I just jump straight to, let me go back to level 3, right? For example, this is how equation look like. Similarly, at the start, we actually add 1, 1, 1, 1, so that you can see. But this time around, after you balance the equation, you have to click on the check button yourself, right? Some form of trial and error might be required, right? Especially when you are getting introduced to this whole concept. Right? So in this case, in terms of balancing of this entire equation, so I'm just going to try out based on what I understand about the formula. Then we'll see if it actually matches the total number, right? So I'm also trying this out because I'm doing it on the go, and it will take some time, as you see over here. Right, so as you can see in this example here, it's pretty hard to balance this entire equation, right? So, but it's okay. There are equations that's a bit harder, but most of the equations should be quite manageable. So in this case, you also realize that it took me a while that I have to speed up the video. So naturally on your own, when you're doing this thing at the start, it might take a while as well. So take your time, go and play around with this entire equation. And then once you're done with this thing, right, do go back to your notes because we are going to try to balance what is on the worksheet now. Right, so I'm going to move back to the notes itself. So after figuring out the simulation, you should be more familiar now with how balancing of the equation should look like. Now, this is a self-check for yourself. Now, if there's a need to balance and you realize that the coefficient, which is the number that you're going to add, is actually a 1, then there's no need for you to change anything on the equation itself. So there's no need for you to put a 1 here, right? So let's try to apply this and see what it looks like. For the first one, iron plus sulfur, right? We can see on the left-hand side for iron and sulfur, I'm just going to use this as my working step so that you can see my thinking process. There's a Fe here, and there's a sulfur here. On the right-hand side, there's a Fe here, and there's also a sulfur here. So actually, they are being balanced. So in this case, it's really a 1, 1, 1. But like what I mentioned, we are not going to put 1, and this will be balanced by itself already. Next, let's take a look at the second example. On the left-hand side, I have a H, 2 of them. I have a Cl, 2 of them. On the right-hand side, I have a H, 1 of them, and I have a Cl, 1 of them. So when I look at this thing, I realize that it's not balanced. How do I balance it? I actually have to put a 2 times over here, right? Then this will actually balance up the number, and therefore the equation here should be a H2 plus Cl2 gives you 2HCl. Similarly, let's try it out for the third one, right? Mg plus O2 giving us MgO. So I have an Mg here, I have 2 of the O, right? So I have 1 over here, and here I have 1 of the Mg, and I have 1 of the O, right? So what can I do to balance out this entire thing? Most likely is that I need to take this entire thing, I need to multiply by 2, and then this number of Mg, I also need to multiply by 2, right? So then this will give you an equation of 2 Mg plus O2 gives us 2 MgO, right? Then let's try out for the third one, actually the fourth one. Alright, so as you take a look at example 4, let's draw it out again. So for left hand side, I have oxygen. Let's say I have these 2 oxygen here, and then I have hydrogen. And then on the right hand side, I realize that I have H2O, right? So I have this kind of drawing. Right, so how do I balance up the entire thing? I do need one more set over here, right? And you introduce me to have one more set over here. Then this will mean that I need to have 2 sets of the H2, 1 set of the O2, and this will give me 2 sets of the H2O, right? And then this should be the balanced equation, right? So do try this out for yourself, 5, 6, and 7, and 8, right? So that you can have a sense of whether you are getting the concept or not. After you're done with this thing, take a pause on the video, go and complete worksheet 4, right? Once you're done completing worksheet 4, you can access the next set of videos to run through the answers for worksheet 4 before you go on to practice 1, 2, and 3 on the notes, and then we'll move on to worksheet 5 together. Okay, the video will pause over here first. Remember to do all the blanks that you see up to this point, and then go and complete worksheet 4 on your own as well. Thank you.